All right, good evening, everyone, and welcome to the Brown Planetarium here at Ball State University. How is everyone doing this evening? Awesome. We kind of lulled you to sleep with that music. I apologize. This is supposed to be a much more energetic event. So let's go ahead and get some energy going in this room here tonight. Who has been here before? Raise your hand if you have been here before. Quite a few of you have been here before. Just to even it out, who has not been here before? Okay, so people have not been here before. Someone was raising both hands, so they doubly have not been here before. That's good to know. All right, so for those who have not been here before, I usually start presenting in the back of the room where the controls are because I control the technology in the theater here. My name is Dana Thompson. I'm the planetarium director here at Ball State University. I've been here at Ball State for over 10 years now, managing the planetarium. But this planetarium isn't that old. We actually had another planetarium in the basement of this building, a 30-foot dome that was really servicing the community since 1967 or so, and serviced about 500,000 people. And then we were like, we need to do more. And so we built this new facility here in 2014, and it is the largest planetarium in Indiana. The largest planetarium in Indiana at about 16 meters across. That's about 52 and a half feet. 52 and a half feet. And what makes it really special is the technology. The technology, some of that technology you can see in the middle of the room here, that's being highlighted. And that is our star projector. Our star projector, it's an optomechanical device. An optomechanical device, that means it uses gears, lenses, LED lights, and more to put up things like the closest star to us out in our solar system. What's that, by the way? Yeah, the sun. There you go. The sun. Yep. Not a hard question there to start with. The sun. And I just turned on our sun. You see it shining in our planetarium sky. Yep. Over kind of on the other side of the sky where you came in. Okay, so we have our sun shining there. We can also put up the closest natural object to us, which is our moon, which isn't up quite yet for the time and day that we're set up to here for our planetarium star projector. And we can put up things like the planets, the closest worlds to us. And we can put up things like the stars with our star projector, of course. 4,000 of the brightest stars that we can make our constellations out of. And you can start to see a handful of these things as we're speaking here. But in order to see everything, we have to make it extremely dark in here, much darker than a movie theater. So things like cell phones usually show up really well here. You're actually going to use your cell phones during this event to vote for your favorite presenter, because this is a very special event that we have here that we host just once every year, an Astronomy Slam, with our presenters sitting up in the front of the room there, getting ready to present their hard work that they've been working on for so many months now. So before we get into that, let me just kind of ease you into it while people are still finding their way with construction and everything and the weather. We want to make sure people can find their way safely into the dome and to some seats. So we actually bring up some light here in the planetarium, mix it together, or really our eyes do the mixing. But when we bring down the blue light and just leave up the red, we should be able to see quite a bit more of what our star projector is projecting. All right, so those bright objects by the sun, what are those? Do you remember? Yeah, we have the planets, the other worlds that we can project. So we have this one that shines really bright. That's the hottest planet in our solar system. What's that? The hottest planet in our solar system? Yeah, some people think it's Mars because that's a red planet, but it's actually Venus. Yeah, Venus, the hottest planet. And then we have this one that's faint next to it. That is Mercury, the tiny planet, the smallest planet in our solar system. Let's go ahead, speed up time here, because we can go any time of day, any time of night, plus or minus 10,000 years, and see what the sky looked like in the future, or will look like in the future, and what it looked like in the past. We actually went to yesterday in our system here. Yesterday night, you could see this wonderful thing by the moon. So here's our moon here. And right above it was another planet. Do you remember what planet that is? Jupiter. Yep. If you follow us on our Facebook page or any of our social media pages, you saw a picture that I snapped in the parking lot after I got off of work last night. We have Jupiter shining above our moon. Okay, so we have the bright planet Jupiter. But this was last night. The sky changes from night to night. So let's jump forward in time and go to tonight. The moon moved its position in the sky as it orbits our planet, but everything else kind of stayed the same. Okay, so we're going to explore more of this during this night sky during the presentations that you'll hear in just a minute. Our star projector down in the middle of the room is not alone. We have 2 digital projectors on either side of it, and they put up things like labels for our moon. And if we speed up time, these 2 pieces of technology, they talk to one another. They move along the dome together. And we can do more than that. We can put up things on our entire dome and make our whole dome kind of like a movie screen. Bringing down the red lights even more. Hopefully everyone's in for the most part. We can start to see some more detail here in the planetarium. So our system is very unique. We have these 2 pieces of technology. It makes it a hybrid system. Not a lot of planetariums have this setup. We're one of only about a dozen planetariums in the United States that has this kind of setup here in Muncie, Indiana at Ball State University. Why do we have more than just the digital? Because the digital can do stars. Well, the digital puts up things at a resolution of 4K, but the optomechanical puts up a night sky, an amazing night sky, which you'll see with our first presenter, with a resolution equivalent to 70K, 70K. So it just creates a realistic night sky. So this is the technology that we'll use for this evening's show. A lot of the programs, the visuals that you'll see for the presentations tonight were directed by our students, but there's one student who actually programmed out their visuals, and we'll make sure to highlight them when they are introduced, okay? Okay, so we have 4 student presenters tonight competing for Astronomy Slam Champion. If you're not familiar with this event, we have 4 awards. There's Best Overall, Best Energy, Most Thought-Provoking, and Most Visually Engaging. You all got a program when you came in, and those are written out. If you open it up, bottom left, you can see tonight's awards. There's Best Overall, Best Energy, most visually engaging, and most thought-provoking. So keep that in mind because you're going to be voting on who gets what at the end with the QR code there or the link there. And then if you need to do a write-in vote, if you don't have the technology to cast it with the Google form that we'll link you to, that's not active just yet, then we'll hand out pens for everyone, okay? So for those who need it. Otherwise, we'll get the votes through the online form, and we'll tally them up during some Q&A. So the process is we have all the presenters present their 10 minutes. They only get 10 minutes apiece. Then we'll open up the voting, give you some time to vote. Then we'll do a quick Q&A, and then we'll tally the votes during the Q&A and release the awards or give out the awards. All right, the reason why we don't do a Q&A after each talk, in case you're interested, is because we really want to highlight the 10 minutes apiece and really have that be the highlight of the competition part of everything instead of getting the Q&A kind of thrown into it. All right, so one of the reasons why we're here is to really highlight our students in the Department of Physics and Astronomy. We have amazing students, not just undergraduate students, we have master's students who are getting their master's degrees in physics here in the Department of Physics and Astronomy, which the Planetarium is a part of. And they do amazing work, and we want to highlight that and give them a venue to do some friendly competition in front of a supportive audience. So I know that all of you will be supportive during their talks and get them hyped up for each of their presentations. But who will really get us hyped up is Nicolette here. So Nicolette, coming to the front of the room, let me bring up some light for them. Nicolette is our Astronomy Slam Champion for 2021. She won last year's Astronomy Slam, and she's going to be, give her a round of applause. She is going to be the MC for this evening. So she's going to really introduce her colleagues and her friends, and get them excited to present in front of you. And I know Nicolette will do an amazing job because she's already won. She's an award-winning student, so of course she's going to. All right, so I'm going to turn it over to Nicolette and let her introduce our presenters.
Check. Cool. Hello, everyone. As Dana's mentioned, my name is Nicolette Terrasciano. I am the current reigning Astronomy Slam Champion of 2021. Of course, I will be passing my title and crown to one of our lovely presenters tonight. Of course, willingly, I promise. I would just like to thank you all for coming tonight. It is so amazing to see all of your faces here with us. When I presented last year, there was about 3/4 of you here. So we have another quarter of people coming, which is amazing. I want everyone to be able to see what our presenters got. And trust me, it's a wonderful sight to see. You definitely came at the right place at the right time. A little bit about me. I'm an undergraduate student here. I have a double major in astronomy and physics with a mathematics minor. And for those who saw Astronomy Slam last year or did not, a refresher, I did a presentation on exoplanets, mainly outside of our solar system, and talked a little bit about Kepler and TESS. So without further ado, you're not here for me. You're here for our lovely presenters here today. So let me introduce them to you first, and then we'll get our first presenter started. So we have Kenya Cole, we have Caleb Whitcomb, we have Kyree Standifer, and we have Madeline Shepley. All of them are friends and colleagues, so I wish them the best of luck, and you know that I am here in the dome with you giving my full support, so remember that, don't be nervous. Without further ado, I would like to introduce our first presenter, Kenya Cole, and I want some hype, people. I want some clapping hands, you know, woo-woo! Make her welcome to the stage.
So hi everyone, I'm Kenya Cole, and as I'm sure all of you know, there are tons of things to learn about space and what we can find up there. During my talk, we're going to take a look at our night sky after sunset and maybe learn a little bit more about what we can find when we know what we're looking for. I'm hoping everyone here knows what Jupiter and Saturn are because we are going to start off by focusing on these two planets. So Jupiter is over here in the southern part of our sky. It is to the right or west of our moon. So let's take a closer look at Jupiter. Jupiter is the 5th planet from the Sun and the largest planet in our solar system. In fact, its mass is more than 2.5 times that of all the other planets in our solar system combined. Jupiter is also a gas giant. This means that it doesn't have a surface that you could land a rocket ship on. The planet is mostly swirling gases and liquids. Similar to our Sun, Jupiter is made up mostly of hydrogen and helium, almost like it's a failed star. Some of you may know what this is. It's called the Great Red Spot. I personally would have given it a more original name, but I wasn't chosen for the job. So does anyone know what's going on here in this spot? I think I heard it. Yeah, it's a giant storm that's been going on for hundreds of years. You may recognize the shape of it because it's similar to the shapes of hurricanes that we see on the news. It can also change slightly in size, but it has always been significantly bigger than our Earth. Here we can see just how small the Earth is compared to Jupiter. Something else interesting about Jupiter is that it spins much faster than Earth does. Jupiter makes one whole rotation in about 9 hours and 55 minutes at the equator, and this means that a day on Jupiter is only about 10 hours rather than 24 like here on Earth. Okay, so now we're going to take a look at a more recent picture of Jupiter. So this picture was taken by the James Webb Space Telescope. Something we notice from this image is that Jupiter has rings. As of right now, we know that Jupiter has 4 sets of rings. These rings are made up of dust. When small meteors impact Jupiter's smaller inner moons, the impact isn't large enough for the moon's surface gravity to keep the dust particles from moving away. So instead, the dust makes its way into orbit around the planet, and that's what forms the rings around Jupiter. Speaking of moons, so far we know of about 79 moons in orbit around Jupiter, but only 53 of them have names. Don't worry though, I won't stand here and list them all off for you. So here we can see the different ways and directions that these moons orbit Jupiter. And these pictures are the 4 Galilean moons. From left to right, it's Io, Europa, Ganymede, and Callisto. The one we'll focus on is called Europa, which was recently visited by the Juno spacecraft that's in orbit around Jupiter, giving us new images of the icy moon. So Europa's surface is mostly made of ice. In fact, underneath this ice surface is what is believed to be liquid water. This is not just a little bit of water, though. Europa is actually covered in oceans. And although this moon is a little smaller than our own, it could have up to twice as much water as all of our oceans on Earth combined. Because of these vast oceans, we find it to be one of the more promising places to begin looking for life beyond Earth. Jupiter is a very interesting planet, but I think it's time for us to go home. So while we're back on Earth, let's take a look at our night sky again. So far, we found Jupiter over in the south. Another planet in our night sky is Saturn, which you can see in the southwest. Now, I know we just took a big trip, but if it's all right with everyone, I think we should head up to Saturn to take a closer look. Saturn is the 6th planet from the Sun and the 2nd largest planet after Jupiter. Similar to other planets in our solar system, Saturn has rings. In fact, that's what Saturn is known for. However, the difference is that these rings are massive and much brighter in comparison to other rings from other planets such as Uranus, Jupiter, and Neptune. Let's take a look at these incredible rings around Saturn. Something that most people don't know is that each ring orbits at a different speed around the planet. And these rings are made up of billions of pieces of broken up chunks of ice and other materials such as dust. The ring particles mostly range from tiny dust-sized icy grains to chunks the size of a house. Interestingly enough, a few particles within these rings are as large as mountains, which can clump to form moonlets. One moon we find within these rings is called Pan. Pan is very small with a mean radius of about 9 miles, and it's shaped like a flying saucer. There are actually quite a few similarities between Jupiter and Saturn. If you remember, Jupiter is made up mostly of hydrogen and helium. This is the same for Saturn. Saturn is 9 times wider than the Earth, and this comparison would look like a volleyball compared to a nickel. And although Saturn is huge, it is the least dense planet in our solar system. In fact, if it was possible to put Saturn in a body of water, it would float. We know that Jupiter has a great red spot, but Saturn also has a giant storm as well. So this swirling hurricane-like storm is called the hexagon. Obviously, we can see where it gets its name from. This storm is located at Saturn's North Pole. It's also very large, about 20,000 miles across, with winds around 300 miles per hour. With a diameter that is double the width of Earth, and an unusual but naturally made shape, it's still somewhat of a mystery as to why it has maintained its shape and its extremely high winds for decades and maybe even centuries. We can finish with Saturn by discovering what Saturn eclipsing the Sun can look like. In this spectacular view, we can see how when Saturn is in front of the Sun, Saturn's atmosphere and its rings appear to glow. In fact, from this angle, we can even spot Earth in the background. Here we are on the upper left side of the rings. How incredible is it that we can see this even though these planets are nearly 885 million miles away from each other? Speaking of which, who's ready to head back to Earth? I know I am, even though I love to look and learn about these planets in our solar system. So, back on Earth, we have a couple more things to check out. For instance, our moon is shining bright to the east of Jupiter. It's not quite a full moon yet, but it is what we call a waxing gibbous moon. It will be full in just a couple of days on Tuesday, November 8th. That morning, some people will be in for a treat because it is a total lunar eclipse. This is what most people refer to as a blood moon because it appears red in the sky. So if you look over here, well, maybe. Yeah, so it's going down right there. So this part of the eclipse will begin shortly after 5 a.m. and will go until sunrise on Tuesday morning. If you go out to watch this event, or if you go out anytime this year, look for a cluster of stars called Pleiades, also known as the Seven Sisters. If we start up in the south and we move over here, this cluster of stars right here is Pleiades, or the Seven Sisters. So there are many more stars in this cluster than what we can see with our eyes. Here we can see those stars with the amazing technology that was used to take this picture. So thank you all for coming tonight. I hope you enjoy the rest of our presentations, and be sure to check out the sky maps that we have available. Thank you.
One of my favorite things about working at the Charles W. Brown Planetarium is that my colleagues always seem to teach me something, always. And this presentation actually taught me something new about my favorite planet. I had no idea that Saturn had a storm. That's amazing. Thank you so much for clapping for Kenya. We always loved our appreciation for our friends and colleagues here. I will need the same energy for our next speaker, though. You know, we need to keep the energy going. It's Slam, right? It's Astronomy Slam. So let's give it up for Caleb Whitcomb, everybody. Thank you, thank you.
Hello everyone, my name is Caleb Whitcomb, and I'll be talking about the life cycle of stars. Just before me, my friend Kenya showed this image of the Pleiades, which is a cluster of young stars that form very close together. Tonight, during my talk, we will explore how these stars are thought to have formed. Every night, we look up at the night sky and see an overwhelming number of stars, ones that even the ancient Greeks could see over 2,000 years ago. Throughout history, people have asked what stars are made of. How are they born? What happens when they die? To help answer these questions, we will take a journey towards the constellation of Orion the Hunter to see the birthplace of stars. This here is the Orion Nebula, which, like other nebulae, is a cloud of cold gas that is made up of mostly hydrogen and other elements. It is in these clouds of gas that stars can start to form. These cold clouds of gas heat up when stars begin to form, lighting up the nearby gas. Now in the universe, we have a force called gravity. Gravity is what causes objects to fall and makes our planet orbit the sun. This force also wants to make matter clump together. This is especially true in cell nurseries. As these clouds clump together, the hydrogen atoms keep knocking into one another, and this causes the gas to heat up. As the gas rises in temperature, the cloud wants to expand, counteracting the force of gravity. This stage is what we call the protostar. Eventually, gravity starts to win over, and the cloud starts to ignite. The cloud of gas has fully become a star. These stars are surrounded by electron material that can become planets, moons, and other objects. Now that we know how a star is formed, we will see how stars actually work. Here we can see the interior of a star. As the star produces energy, the star experiences a war of forces. The gravity of the star wants to pull the outer parts inward, and the inner parts of the star are so hot they want to create a force of pressure which counteracts the force of gravity. These two forces balance each other in a process called hydrostatic equilibrium, which keeps the star stable. To see how this energy is produced, we will travel to the innermost part of the star, the core. The core is, for most of its life, made up of hydrogen. The star is powered by a process called nuclear fusion, which is when protons are squeezed so tightly together that they've been squeezed so hard that they form a new element known as helium. In the core, the protons want to escape from each other due to their positive charge, but the core is so dense the protons are being squeezed so tightly that it overcomes their repulsion due to their light charge. When this happens, the helium atom emits a packet of energy known as a photon, which we know of as a particle of light. This photon then travels from the core to the star's surface, which can take anywhere from a few thousand years to millions of years to happen. This is because the photon has to travel to the star's surface while colliding with millions of other particles. During the main part of its life, the star fuses hydrogen in its core. This is helium, the process can vary depending on the star. Here, we have a star cluster, which has stars of many colors and varying masses. The hottest stars are the most massive and are bluish in color, while the least massive stars are the ones that appear to be red. Our sun sits in the middle of this range, being an average star with an average size and average mass and average temperature. We can determine how long a star will live based on how massive the star is. The blue, most massive stars run through their fuel much faster, so they can only live for millions of years. Stars like our sun can last an average for billions of years, but the least massive red stars have lifespans that are longer than the current age of the universe. Despite the incredible lifespans of stars, they too must come to an end. As stars age, they burn to the hydrogen in their cores, turning to helium. However, once most of the hydrogen cores turn to helium, the energy produced cannot stay above the pull of gravity. The star begins to contract, causing the core's outer shell of hydrogen to start burning, which in turn causes the helium core to begin turning the helium into carbon. This process causes the star to expand, turning to what is known as a red giant. While in this phase, the core starts to fuse helium into heavier element, fuse helium core into hard carbon. But for stars like our sun, the core is not hot enough to fuse carbon to heavier elements. At this point, the core starts to blow away the outer layers of gas, creating what is known as a planetary nebula. The leftover core turns into what is known as a white dwarf, which, despite the original size of the star, is only about the size of Earth. White dwarf at the center of these clouds are what make them appear to glow. Stars much more massive than our sun, the ending is more dramatic. As the star's core keeps heating up and producing heavier elements, the energy produced becomes smaller and smaller. This stops at iron. The majority of the star's core is fused iron. The core attempts to fuse iron into a heavier element. Unfortunately, the iron cannot be fused, and this creates an imbalance. Gravity wins, and the outer portion of the star begins to collapse at the core. This leads to an explosive event known as a supernova, one of the most energetic events in the universe. The energy produced in this event in a matter of seconds is greater than all the energy produced by our own sun in its entire lifetime. Supernova events can produce heavier elements than iron, and these elements can be pepper other nebula. The leftover core can become one of two objects, depending on how massive the star was. The most massive stars can become objects that are so dense, the gravitational pull is so strong that not even light escape. You know them as black holes. Least massive cores collapse into what are known as neutron stars, objects that rotate extremely fast and have some of the strongest magnetic fields in the universe. Even though stars will eventually end their lives in dramatic fashion, this isn't the end of the story. Leftover elements from these stars can find their way into new stellar nurseries, enrich this nebula with heavier elements to form new stars along with their own sets of planets, moons, and asteroids. And maybe, just maybe, on one of these planets orbiting these stars, the conditions will be right for life to begin, continuing the saga of the universe. So when you look up at the night sky, remember the journey the matter around you took to get here, because the trees, the town, the planet we live on, you and me, all began as a bunch of little elements in the core of a star that is long gone.
Thank you very much, Caleb, for that lovely presentation. And thank you for giving us a time frame for all of these crazy events, because when my grandfather was speaking to my sister about this kind of stuff, she didn't realize that it was happening billions of years from now. She thought it was happening right this second. And from that day forward, she thought astronomy was quite terrifying. Luckily, she has me to explain some things and make it a little less scary. So without further ado, we are going to get our mic set up for our next presenter, and he is a lovely friend and colleague, and I look forward to his presentation today. Give it up for Kyree Standifer.
Hello, everyone, and welcome to my night sky campout. As we sit next to family, friends, loved ones, we can all take a breath and be thankful for the air around us and the beautiful picture we have every night, the night sky. As we look up, we see bright lights looking down on us, stars. And from here, it seems like they're kind of lonely. When we look up, it seems like all of the stars are close to each other, but we actually know that there are millions, billions, or even trillion miles away from each other. But what if I told you that they weren't alone? And like our own sun, they're accompanied by planets. And in fact, we've even found some of those planets. This is a video brought to us by NASA about all of the exoplanets that we've found so far. But hold on. What is an exoplanet? Does anyone have a guess? Exactly. An exoplanet is just a planet that's outside of our own solar system. So let's relax and watch what we've discovered over the years. It's crazy to think about that. We found over 5,000 exoplanets, and there are potentially millions more out there in our galaxy. But you know something else that I find interesting? What if in another exoplanet far from our own solar system, we can sit outside, right around our campfire, breathe in a nice breath of air, and just live our own lives? Is there an exoplanet out there that could sustain life and probably already have other life forms on it? Are there Earth-like exoplanets? However, let's back up and look at our own solar system, because we know not all planets can host life. Take a look at Jupiter, a planet that we've discussed with one of my previous colleagues. Jupiter is a gas giant, a planet mostly comprised of gas. So even if we were able to survive in Jupiter's atmosphere, the air encompassing a planet, what would we even live on? Because it's just gas. Jupiter doesn't have a true solid surface. But it's okay, because even though we don't have many examples of livable planets in our solar system besides our own Earth, we have some prerequisites that'll help us identify what we could potentially live on. To understand this, we need to understand the habitable zone, a region in which encompasses the star and helps us dictate what planets could potentially be able to host life. You see, a planet that's too close to the star is just too hot. And a planet too far away is too cold, neither of which are good situations in order for life to be able to sustain itself. But if we look back into Goldilocks and the Three Bears, not too hot, not too cold, but just right. Those planets in that habitable region are just right and have the best possibility for being able to host life. However, just because a planet is in the habitable zone, we know that it can't always host life. As we look up, Venus will fly over us. A planet not in the sun's habitable zone and affected by a runaway greenhouse effect. Because of this, we know that Venus is too hot, too gaseous, and too acidic for life to exist. But unlike Jupiter, it does have a solid surface. But it's molten and riddled with volcanoes, possessing over 1,600 major volcanoes. And let's not forget about Mars. As we look up, we can see what we believed Mars to look like in the past with water. But as time moved on, Mars lost its atmosphere, and along with it, its water. And let's not also forget that even though it's in the habitable zone, it's on the far edge, meaning that it's much more colder than life on Earth. But wait, I mentioned something earlier. Water. Why do you think astronomers use water to help dictate whether or not a planet can host life? Any thoughts? You can go ahead and speak up.
A lot of the chemicals to kind of create protocells and ancient life kind of come from the oceans.
Interesting. I really like that answer, and that is true. You see, water is universal, and water is needed by a lot of us to sustain our own life. We need water to survive, as well as our pets, animals, and plants. Without water, life simply just can't exist. But now that we have gained some knowledge about understanding what can make an exoplanet livable, let's apply that knowledge to a different system outside of our own solar system through the Aquarius constellation, 40 light years away, or over 200 trillion miles, which doesn't sound like a fun road trip, but we're already here. This is TRAPPIST-1, a star system that has 7 planets orbiting around it. And we're going to use that knowledge to see if any of these planets are potentially livable. We can't truly see what they look like, but we can still use what we know about the habitable zone. So let's start with Planet B. As we see, Planet B is not within TRAPPIST-1's habitable region, and therefore, it's going to be too hot. There's no way life could truly sustain it. Now, Planet C is a bit more interesting. At first glance, it seems like Planet C isn't within the habitable zone. But a planet's orbit, the path that it takes around a body, isn't always completely circular. And because of that, we can see that Planet C is actually fluctuating in and out of the habitable zone. Of course, it doesn't mean that it has the highest possibility of being able to host life, but it is something interesting to think about. And next, we have D, E, and F. All of those 3 planets exist within TRAPPIST-1's habitable zone. But of course, as we know from Mars and even our own moon, just because something's in the habitable zone doesn't mean you can live in it. If it's too far away, it could be colder than normal life, and all sorts of different applying effects. No atmosphere, no water. And then last but not least, planets G and F, outside of the habitable zone. We know that these are too cold, they're too far away from the star, and unable to support life. So pat yourselves on the back. We just went through a different star system and found some potential candidates. And above me is an artist's rendition of a habitable planet. But of course, it's just a rendition. We don't know. But what we do know is that there's 100 to 400 billion stars within the Milky Way galaxy. And if each one of those stars had at least one planet orbiting around it, And if it was a 1 in a million chance that an exoplanet could be deemed as livable, then we have thousands of livable exoplanets within our own Milky Way galaxy. And that's not all. What about the entire universe? Using modern technology, we can assume that there are 170 billion galaxies, but we know technology isn't perfect. And there's potentially trillions more. So, if we combine all of these galaxies, livable exoplanets based off of Milky Way galaxy, we'd have thousands upon thousands of habitable exoplanets. But here we stand, back on Earth, around our cozy campfire. And although it seems like we're settled here on Earth, I think it's pretty fun to think of what would life be like on another exoplanet, far away from our own solar system. So I hope that after tonight, every time you look into the night sky, you think about the vast amount of stars within the expanse of space. And each one of those stars having a planet orbiting around them. And maybe, just maybe, as you look out into the night sky, someone else, another life form, is looking up into the night sky right with you. Thank you.
Wow, that was truly amazing. I really love the campfire. It makes me really, really cozy in here. But I'm going to ask you guys a question, and I hope you guys can respond for the answer for me. My physicists and astronomers definitely can. So, energy is what? I heard someone said conserved. So what that means is that the energy that we started with at the beginning of this program is the exact same energy that I want to end with, okay? Because I heard some mediocre clapping for before. You know, we got to conserve that, right? So our final speaker tonight is Madeline Shepley. So once again, what we started with, we got to end with. So let's welcome her to the stage with the same energy, right? Thank you.
And I'm going to jump in here from the back of the room really quick. This is Dana again, the director, before Madeline gets started. And just remind everyone that we did have one presenter who programmed their visuals for the most part. And that was Madeline here for the visuals that you'll see. She did about 90% of the programming for the visuals here. So I hope you enjoy them.
Well, good evening, everyone. I hope you enjoyed all my lovely colleagues' presentations. We had some awesome concepts presented and some awesome visuals and just awesome content in general. As I was introduced, my name is Madeline Shepley. I'm a graduate student here in the Department of Physics and Astronomy. And more importantly, I'm going to be your guide for your next astronomical adventure, so I hope you all are ready to go on that adventure. Ready to go? Yeah, love that enthusiasm. So, let me begin by posing a question. Have you ever felt like you were in your own little bubble? Feel free to raise your hands if you have. See some hands. Well, me too. And it turns out, if we actually look up at the night sky, we actually kind of live in our own little bubble. And that bubble, astronomers like to call the celestial sphere. Now, fortunately, the planetarium is like a time machine, and we can fast forward time like we're doing right now to get a closer look at our celestial sphere. Now, up at the front of the dome, you might have noticed this little N right here. That's N for north. And then if we go all the way around here, we got the W for west. And we have it oriented that way just for the ease of viewing of what I'm about to show you. Now, you might have noticed some other things up on the screen that is normally not there. We have these orangish looking lines that, I don't know about you, they kind of look like a bullseye board for darts. And there's a reason for that. So, if we kind of break that down, first thing you might notice is we have these concentric circles like that, like that, like that. They kind of look like celestial latitudes. And those celestial latitudes are what astronomers call declination. Now, there are some other lines here, like so, that intersect those concentric circles. And those are kind of like celestial longitudes, which what astronomers call right ascension. Now, all of those right ascension points, those right ascension lines, they intersect about halfway up the dome at this point. And that is what astronomers like to call the celestial North Pole. And if you were thinking about this pattern that I've established for you, that celestial North Pole is a lot like the terrestrial North Pole we all know and love, except the celestial North Pole is a point in the sky, not a point on the Earth. Now, you might be thinking, if we have a North Pole in the sky, do we have any stars that easily mark this for us? And indeed, we do have such a North Star. Does anyone know its name? Awesome, I heard it, Polaris. And in case you haven't already noticed it, if we go all the way up here, very near where all the right ascension lines intersect, that tiny little dot right there, that's Polaris. Now, all of these things come together to give us the illusion, much like many ancient civilizations thought, that we are at the center of the universe and that our night sky literally revolves around us. It gives us the impression sometimes that all the stars and deep sky objects that we can see are all on the same sphere of some arbitrary distance, hence the name celestial sphere. But I'm here to show you that that is indeed not the case, and that the universe is wider and larger than we can even imagine. You may have noticed that there's one other thing up that's highlighted that I have not talked about. And if we go all the way up here, does anyone know what this is? It is a constellation. Love the enthusiasm. Anyone know what specific constellation this is? I think I heard it. It is the Big Bear or Ursa Major. So our friend Ursa Major, I have him up there because he's gonna be our guide with me and a little bit of a reference point as we fly around from place to place to see the scale of the universe. And you'll have to let me know if he still looks like a bear when we get to our destinations, because that's kind of important. Now, as we fly out to the edges of our solar system, you will see that Ursa Major doesn't change very much at all. He still looks like the same old constellation that we know and love, even hundreds of millions of kilometers from our tiny blue dot that we call home. Now, you might have noticed that there are these lines right here. And these lines, those are orbit lines for a bunch of the different objects. And as we pass each one by, it's like we're passing by Mars, Jupiter, Saturn, yada, yada, yada. And that is just so that we can get a sense of the scale of our own solar system. But what if we fly out a little farther? Say, to the closest star to us besides the sun. Does anyone know what that star is? Feel free to shout it out if you know it. I heard a few people shout it. Awesome. Proxima Centauri. What will Ursa Major look like if we go to Proxima Centauri? Let's go on an adventure and find out. Be sure to strap yourselves in. It's a little bit of a bumpy ride. Or well, mostly smooth. Our friend Proxima Centauri is one of 3 stars in the Alpha Centauri system, a star system that is a part of the constellation Centaurus. It is only a short 4.25 light years away, though that's still mind-bogglingly far away compared to everyday distance scales for humans. Now, if we look all the way over to your right, we'll see our friend Ursa Major, and Ursa Major looks relatively recognizable here still. Like, if you look over here, you'll see that our Big Dipper asterism here, the ladle and the spoon, whatever you want to call it, still looks relatively the same. The only real difference that you might notice is that that front kind of paw, leg, kind of looks like Ursa Major is stepping very gingerly, almost as if to avoid stepping on something unexpected and unpleasant, which I don't know about you, but I don't want to step on something that I'm not aware of. That would be very unpleasant. So now that we've established that Ursa Major is noticeably different, but not unrecognizable at Proxima Centauri, what if we went a little bit further? Let's go visit our friend Vega to find out. Vega is a star about 25 light years away from the Sun in the constellation Lyra. It is still a relatively close star, but clearly much farther away than Proxima Centauri. Now, the lines in Ursa Major, if you look all the way over to your left, somewhat high up on the dome, you'll notice that Ursa Major has clearly changed and is not quite so recognizable anymore. If you look over at what we know to be the Dipper constellation, the ladle part kind of looks more trapezoidal. And then we have the legs look somewhat recognizable and the tail, but if you look all the way up the front of Ursa Major, I don't know about you, but that doesn't look like a bear to me. That looks like just a jumbled mess of lines. So very clearly at Vega, the constellation lines have truly started to warp for our friend Ursa Major, and they're starting to become not recognizable. But what if we go even farther? Will we still be able to connect the dots between the stars of Ursa Major? Let's find out by visiting our friend Deneb in Cygnus the Swan. Deneb is a staggering 2,615 light years away from the Sun. Talk about needing a long vacation if you visit this star. You would have to cash in so many PTO days, like it would be insane. Probably wouldn't have any anymore. So you'd have to be real committed to go visit Deneb. If you look as our star in view slowly comes into view, you might notice that we have some bluish lines there. Well, that's our friend Ursa Major's constellation lines, and if you look at them, it is clear that at this distance from our home planet, you would be lucky to just be able to recognize the Ursa Major stars easily, let alone connect the dots with them. At this point, we are so far away from home that the terrestrial notion of constellations makes no sense anymore. If you wanted to make sense of a night sky around Deneb, like we do on Earth, you would have to draw your own constellations and make new ones. So let's say we could connect the dots between these three stars and we would make that our new summer triangle. Over here, maybe we could connect the dots right here. And I don't know, let's make that a new, let's make it a cardinal because we're at Ball State. Then, I don't know, let's see. Let's connect these ones. I'm going to call that the bell tower for Ball State. So we would have to just connect our own dots to be able to make sense of the night sky. I'm sure you could come up with some more creative ones than me. Now, these stars that we visited are only a tiny fraction of the hundreds of billions of stars in our galaxy, and while 2,600 light years may seem like a lot, that's a tiny distance compared to what the true scale of our galaxy and universe is. And we can see that as we zoom out from Deneb to see our galaxy from an outsider's perspective. Our galaxy itself is about 100,000 light years across. To put that into perspective, our sun is only 26,000 light years away from the center of the Milky Way. So, as you can see, 2,600 light years really is chump change compared to the grand scale of galactic things. Mind-boggling, right? Now, if you thought that was mind-boggling, what if we went beyond our galaxy into the wider universe? As you can see, as we fly away, there are many other galaxies, and even our own beloved galaxy is just a small dot in the vast sea of galaxies, of which there are billions and billions in the observable universe. So next time you look up at the night sky, don't forget that there's a whole world out there beyond our celestial sphere. And I'm just going to disappear to let you guys take that all in. Cool? Awesome.
Wow, that was something else. I actually started getting interested into astronomy when I was a wee child. My sister would take me stargazing every night as a way for us to bond. And it wasn't until college that I really understood that space is 3D. And this is a really great representation of what that really means. Because when you say space is 3D, I don't know about you all, but my brain can't print that out in my head. I have no idea what that means. But that was a really great presentation. Thank you very much, Madeline. I would like to tip my hat off to all 4 of these presenters. That was absolutely fantastic. Thank you again. That was amazing. I am really lucky I don't have your guys' job because I don't think I'll be able to decide who a champion is because this is just too tough. But I will pass the mic to Dana because we're going to explain the voting once again to make sure we all know how to do it.
Yeah, the voting form is now active, and the QR code or link, if you need to type one in, is on the inside of your program. 1 vote per person, please. It is on the honor system. And if you can't access that, then we will pass around pens. Nicolette has a handful of pens, and then our Planetarium show specialist, Melanie's walking around with pens too. So if you need to write in your vote, go ahead, raise your hand, and we'll get it writing utensil unless you already have one. And once you have it all written out, you can put your brochure, your program up in the front of the room on the table where the awards are, and then we'll tally them up. Okay? We'll give you a second to focus on your voting, and then we will open up a Q&A. So if you have any questions for our presenters, we'll give you a microphone. You can ask your question, and then we'll give the mic to each of the presenters to answer them. And then what we'll do after we award the trophies is we'll release people into the lobby to enjoy our lobby snacks and everything, okay? All right, so we'll do Q&A in just a bit. Anyone else need a pen, writing utensil, or anything like that? Raise your hand. There's some in the front row. Okay, so while everyone's doing that, remember we have awards for Best Overall, the Astronomy Slam Champion, Best Energy, Most Thought-Provoking, and Most Visually Engaging, so that everyone here gets an award tonight. Our awards are little trophies in the front there. If you look closely at them, the little golden trophies for the 3 sub-awards are painted. I just painted them today with like an eyeball for Most Thought-Provoking. Most visually engaging. I'm getting it confused now. Most visually engaging, a lightning bolt for best energy, and I painted the little light bulb for most thought-provoking. But then we have a really nice trophy for the overall slam champion. All right, so those presentations were amazing. I really enjoyed helping all the students put together the visuals, helped Madeline put some final tweaks on it, but really she did the bulk of the work there for those. So we're going to keep getting those votes coming in, tally them up. It's going to take a little bit. So while we do that, we're going to ask some questions to our presenters. We can start that with Melanie. I'm going to pass the mic off to you and let you ask a question if no one else has one to start with, okay?
Excellent. If anyone does have any write-in votes, feel free to bring them my way, and I'll go ahead and get started tallying those. Do we have anybody that maybe has any questions for our presenters to start here? Yeah.
Hi. So I've got a question on the life cycle of our stars. When we know that they begin and die like everything else, how can you judge the temperature of the life or the death of the star? How do we know that?
So for judging the temperature of the star, we often tell by sometimes by the light we actually see from the star. Certain stars, as I mentioned before, that are hotter tend to be more bluish in color. think of it similar to like when you're looking at see a welder on TV. They don't use a red flame; they use a blue flame. So blue tends to indicate higher temperatures. So.
Excellent. Thank you, Caleb. Any other questions for our presenters? All right, I see a hand in the back here. And I will be coming around to collect votes as well.
Thank you. This one's for Kyree. So we're carbon-based life forms. What do you think the odds are that there could be other life forms out there based off of atoms of similar chemical properties, such as silicone or lead or something along the same lines?
That's a really good question. I actually really enjoyed it. And the truth is, I just don't know.
When it comes to aliens, that's usually the answer we have as of now. If anyone else has any suggestions on what these aliens could look like, feel free to draw one and hang it up in our gallery. Or check out some of the aliens that some of our kids that have been visiting us have been drawing. They're very entertaining, very creative. All right, thank you for your question. Any other questions for our presenters here? All right, I do have a question for Madeline. So what made you so inspired to come in and program your own visuals? Because I know that was something you were really interested in doing.
I'm glad you asked. Okay. So the inspiration behind what I did kind of started back last semester. I worked on this really cool, the Planetarium in conjunction with I believe the American Association of Variable Star Observers put together, I know at least like 10 or 11 of them are done, but variable star like short dome shows. And I worked on the one on Myra, which is in the constellation Cetus. And so in the process of doing that, there's this one scene about halfway through where we kind of do a similar constellation warp, and you can see like kind of like what happened with when we went to Vega. You can see the lines actually warp as you fly to the star, and I was just like, whoa, that's so cool. And then this summer, I had worked on a project for my thesis in doing these presentations, these planetarium experiences for Dr. Todd Vaccaro's A100 class. And one of them is also a constellation warp, and I got to do that, and it looks so cool, and I'm like, I gotta do a presentation on this. Plus, since I got to do and work on the visuals for those, I was like, I want to program my own visuals this year with a little bit of help from Dana, because I'm a novice, and sometimes the software doesn't exactly want to do exactly what you want it to do, and usually Dana knows how to like tease it a little bit to make it work the best that it can. And I don't know, it was a lot of fun to put together.
Yeah,
So-
flying manually through the universe isn't too easy, is it?
Yeah, it took me, I don't know, it took me a few hours to figure out some of them, just because I would tweak one thing and it would fix what I wanted it to fix, but then things elsewhere would get thrown off, and I'm like, come on, man.
It definitely takes a lot of time. And it showed. You did a great job, Madeline. Can we get one more round of applause for our presenters here? Excellent. We are still working on tallying those votes. Does anyone else have any write-in votes they'd like to hand in? Nicolette, could you help me? Excellent. Any other questions for our presenters? If not, I do have one for Kenya here, not to put you on the spot. So anyone is able to participate in the Astronomy Slam. We do not require students to be in the Department of Physics and Astronomy. Fortunately, many of them are. I believe all of them except for Kenya here, who is in elementary education. So I just want to get kind of your perspective on what it's been like to kind of step outside the box and kind of come at it from a unique angle from the rest of our team here.
It's been a really cool experience. I assume it's a little bit different from my colleagues because I come from a standpoint where I want to teach people and like explain how things work, and so it was a really fun thing that I got to do because since I'm not in this department, I didn't know a lot. I certainly don't know as much as my colleagues do. So it was really fun to be able to teach myself as I was creating the presentation. And so I was just happy to be able to share the information that I've learned with all of you.
All right, any other write-in votes for us here? All right, Nicolette, do you have any questions for our presenters? Coming from the last year's Astronomy Slam Champion.
Actually, yeah. So I got to hang out with them in the back, trying to get all the jitters out, because when you're performing, even if you've done it for a really long time, you still get a little nervous. And boy, were they nervous. How do you feel now? Are you okay? Is the heart rate down? Are we all good?
Yep. We survived, we made it, and we did a great job. All right, I have one last question for our presenters here. Any other questions from the audience? All right, one here.
What is in a black hole?
What is in a black hole? Good luck. Who wants this one?
I'll take it. Okay. The long answer is we don't know. We don't know what's going on, and we actually have a black hole music video, which they basically state that for like 2.5 minutes using Morgan Freeman's autotune voice. So we honestly don't know what's going on. We know what's going on around it, but not really what's going on inside. So
that's kind of the short answer and the long answer. Not only do I not know, not only do they not know, nobody knows. And that comes into play quite a bit with astronomy. Again, we got aliens, we have black holes, there's tons of strange things going on out there. So if any of you are younger learners here, or anybody who's interested in pursuing science, we could use all of the help that we can get, is basically what we're saying.
There is no such thing as a stupid question, by the way. They're not in this dome. It is a nice, okay place. So any questions are welcome.
All right, excellent. We got 2 hands. I'll start here, and then we'll go back to this one.
I'm just curious, for each of the presenters, what is your favorite space movie, and do you think it's accurate?
That's a really good one. All right, Nicolette.
Sorry, I'm the one closest to them. I can hand them the mic.
So my dad already knows this. Interstellar is my favorite space movie. I don't know if it's accurate, but I would say they're giving me thumbs up and nods. So I'm going to say, yeah, I think it's pretty accurate.
Not to sound like a broken record, but actually mine is also Interstellar. I love that film. And actually, they actually had a science consultant on the movie to actually get it pretty accurate. I mean, apart from the last part of the movie stuff, but can't get everything right. But it's pretty accurate to what happened. So, but yeah, that's my favorite space movie.
And of course, to keep the train running, I also love Interstellar. As all of my colleagues said before, it is really accurate until you get to the end. I won't spoil the end. You just gotta watch for yourself.
So, can I say my favorite book? Because Interstellar is also my favorite movie, but I wanted to mention this when Kyree talked about non-carbon-based life forms, and it made me. But I don't know if anyone's ever read anything by Andy Weir. He's I see a hand over. I see some hands in the back. Well, he's mostly known for The Martian, but my favorite science fiction book is Project Hail Mary, and basically the synopsis is, I'm trying to remember what kind of scientist, but one of the main characters, he's a scientist, and he basically kind of gets voluntold to go on a mission to, yeah, he got voluntold to go on a mission to save the Earth, and he makes an alien friend, and that alien friend has, I'm pretty sure, a non-carbon based biology. It's been a while since I read it last year, but it was honestly just the redemption arc in it was great, and the friendship between the two main characters was awesome. So I was like, since everyone else said Interstellar, I felt I had to say something different.
All right, did we have another question over here? Excellent. So the question was, can we watch the black hole music video? All right, I will get back to you on that. I'm going to take one question up here.
So, are there any hypothesis or models or anything about what might lie outside of the expanding universe? What's it expanding into, or if there's any kind of dimensionality outside of it?
Any of our presenters, really quickly? Otherwise, I have something. Good. I can actually give you a book later if you'd like. It is written by a cosmologist that I got to meet. He is a wonderful man, Will Kenley. It is written in the general public reading, so he may be a cosmologist, but you can definitely understand it. He actually studies what happened to kind of help the Big Bang get started, and I think that's what you're asking for. I have a picture of his book in my phone. I will gladly share that with you. Any of our presenters got anything? Okay, great question.
What is your best guess as to what dark energy or dark matter might be?
I will run that to our presenters really quick. Great question.
I am very much so a member of the general public, so I have absolutely not even a clue.
This is just from, my classes with our beloved Dr. Barrington, but the short answer, just like black holes, is we don't really know what they are exactly, but we can observe their effects on the universe. We do know we can see the effects of that. We know that dark matter is there, but we can't really see it, and we don't really know exactly what it is. And we know that dark energy is there, but again, because we can see its effects in the universe, well, we don't really know what it is either. So that's one of the big questions that scientists are trying to figure out right now. So,
unfortunately, I don't know a lot about it either, but what is interesting is that actually is one of my more favorite topics within astronomy. So I'll get back to you maybe 50 years from now.
I feel like my default answer, because I'm not a dark matter astronomer, is to ask the two astrophysicists in the room, because they probably know more than me on that. Maybe, I don't know. Dr. Millis, Dr. Ricardo, you got ideas?
That is the proper way to handle the question, Madeline. Absolutely. But I think that the reason why it's so hard for some of the students to answer that question is because it's a hard question to answer for anyone. We don't really have a lot of information about those objects or phenomena in the universe. So it's a complicated topic. You'll have to come back to some of our planetarium programs to experience the answers of those, or try to, just peek at some of the answers, because we're still trying to figure out those answers. All right, so we have some awards. It was really hard. You all made it really difficult because everyone did an amazing job. But I did my best with tallying up the votes and under pressure, and got on all the write-in votes and everything. I think I did a good job of reflecting what everyone thought. So, Nicolette?
All right, I will turn things over to you, Nicolette. We're going to go kind of through our regular categories, and we will end with the overall Astronomy Slam Champion. So thank you all for voting. Can we get kind of a drum roll? This is very exciting.
All right. So And of course, I'm very happy about this one. Best energy goes to Madeline Shepley. Very, very, very appropriate. Thank you all. Next, we have another drum roll, please. Thank you. Visually engaging goes to Kenya. Okay. Next. I hear it. There we go. Most thought-provoking goes to Caleb. Caleb can correct me if I'm wrong, but I think this is a repeating event. There we go. He just has really great topics. All right, this is the big one, guys. So we got to have a big drum roll. You ready? There you go. A little bigger. There we go. And our 2022 Astronomy Slam Champion goes to Kyree. There you go. Were you trying to replicate Simba there? Or just show it off? Either one works. I immediately thought of Simba. That works too.
All right, congratulations, everyone. Thank you, everyone who was able to help out during this event, and everyone who voted and came out and supported the Planetarium.